Okay, this is the second half of the graphing lesson. In the first half, you learned how to tell whether the function was going up, increasing, or going down, decreasing. You also learned how to figure out where the max and min were. The second part is going to involve the shape of the curve. Every one of the graphs you're going to draw is a polynomial. So it's going to be like a roller coaster. It's just a series of arcs that are connected, but you have to make sure that you draw the shape correctly as it goes up and down. So the concept is called concavity. All right, that's the shape of the arc. You have something called concave up and concave down. Concave up, now I know this looks like I drew just a parabola and a parabola upside down, and that basically is what it is. This is really two arcs though, connected. The shape of concave up, I mean, it looks a lot like a smiley face, and concave down looks a lot like a sad face. So that's the shape that you're going to draw. Now I'm going to show you that it depends on whether it's going up and down. I'm going to draw a couple more for you. All right, so I've drawn 4 of these. I'm showing you what the graph going up, increasing, and concave up looks like. Right? You see that it's half of a smiley face. That's where you would start. The graph's going up. It's a shape, they always say concave up is like a bowl that would hold water. So if you were to try to pour water in here, right, it would kind of catch it. Decreasing and concave up. Now this graph is going down, right? Decreasing means going down. But again, the shape, think of it as smiley face, just split apart. These are the type of arcs you're going to draw when you put together the entire graph, right? Now, concave down, if the graph was increasing and concave down, remember, concave down has nothing to do with the graph going up or down. It has to do with the shape of the curve. I mean, I wish they said something other than down, because if you think down, you think, oh, getting smaller, but it doesn't work that way. So again, if you think this is like half of your sad face, the graph is increasing, it's going up, but the shape is concave down. Now this graph is decreasing, see, it's going down, but again, the shape is like a sad face. All right, so these arcs, these are the only 4 arcs you're going to draw when you make an entire graph. This is what you'll put together. If the graph is going up or down, and concave up or down, then you know which arc to pick. And I'm going to show you how to figure this out. It's very similar to the increasing and decreasing, fortunately. All right, so this is how you're going to figure out what the shape of the curve is going to be. Before I do that, definition. If you have a point where the graph switches, concavity. What the hell is concavity? Concave up or down. If the graph switches its shape from concave up to down or down to up, if the shape changes, that point where it switched is called an inflection point. Okay? I usually write inflex with an X, not a C. So we find concave up and down using the second derivative. Increasing and decreasing was the first derivative. Concave up and down is the second derivative. What's nice about this is that it makes sense. If the second derivative is positive, then the shape is concave up. If the second derivative is negative, then the shape is concave down, and I like that. Positive, up. Negative, down. Same thing with increasing and decreasing. When the first derivative was plus, the graph was going up. When the first derivative was negative, the graph is going down. So it's similar with the shapes. Second derivative positive, concave up shape. Second derivative negative, concave down shape. Okay, so now the steps to do this are going to be almost exactly the same as figuring out increasing, decreasing. You see, this is very repetitive, this problem. It's also very long. I'm going to quickly write the steps for you, and then I'm going to do an example, maybe 2. So like before, when you did increasing and decreasing, there's a lot of steps to this. It's involved. To do increasing, decreasing, you already found the first derivative. You already have it. So now you just need to take the second derivative. So you take the derivative of the first derivative, right? That's the second derivative. You take the second derivative, you set it equal to 0. You solve for x. Usually, I don't want to say every time, usually you only get 1 point here. Most of the time, when you take the first derivative, you get 2 x's, right? When you solve, you get like x squared something. Here, you're just going to get, like, say, 3x minus 6 as the derivative, and then you would set that equal to 0. You'd only get one number. You might get two. You put these number or numbers on a number line, just like you did with increasing and decreasing, and you pick test points in each region, just like you did with increasing and decreasing. You're going to take your test points. Where are you going to put them? You're going to put them into the second derivative. Why? Because the second derivative tells me the shape of the curve. If I plug my test point into the second derivative and I get a positive number, then the shape of my curve was concave up. Remember, you don't give a damn about the number. I don't care if the number is 16. I care that it's positive. I don't care if the number is -7. I care that it's negative. So if you plug into the second derivative and you get a negative, then the graph was concave down. Now, if you switch, definition above, if the graph switches shape, if it switches concavity, you have an inflection point. You're going to need to know that point and plot it. So if you see a switch, if the graph does switch from concave up to down, or vice versa, then you have an inflection point. I told you how I abbreviate it, inflex with an X, even though inflection is spelled with a C. So if you do have an inflection point, if you do switch concavity, you have to plug back where? Into the original function, f of x, and find the y value. How the hell are you going to plot that point if you don't know the y value, okay? So this is the process. I'm going to go through it again with another example, just like I did with increasing and decreasing. Okay, our example. Find where f of x equal blah, 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 blah. You have 2x third minus 3x squared minus 36x plus 1. Find where that graph, that function, is concave up or concave down, and find any inflection points. So I need to figure out the second derivative. First, I'm going to figure out the first derivative. 6x squared, right? Multiplied by the power, subtract 1, minus 6x minus 36. What's the derivative of 1? 0! I can almost hear your voices in my mind, or those are the other weird-ass voices I hear in my mind all the time. Second derivative, 12x minus 6. Yeah, it's going to be kind of annoying. Okay. Anyway, I should have changed that. Too late. That's the second derivative. It's bothering me it's not a whole number because it always comes out to be a whole number, and I'm not going to plug it in. It's going to end up being a half. So I'm going to have to create another example. Okay, so here's the example that we're going to work. Find where f of x equal blah, 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 2x third minus 6x squared minus 36x plus 1 is concave up or concave down, and find any inflection points. Remember, I abbreviate the word inflection with inflex. So I need the second derivative. So obviously I have to take the first derivative first. Power rule, multiply by the power, subtract 1. Multiply by the power, subtract 1. Derivative of 36x, negative 36x is negative 36, and the derivative of positive 1 is 0. I can almost hear your voices yelling out 0 in my mind. Of course, could be the other weird-ass voices that I normally hear in my mind every day anyway. So the second derivative is going to be 12x minus 12. 36 constant, derivative is 0. There are those voices again in my mind. Now, you were supposed to set this equal to 0. Why? I need like a possible inflection point. Now understand something. When you set it equal to 0 and solve, you're going to get this number. That number may or may not be an inflection point. You might get a number and then the graph is concave up, and then you don't have an inflection point. So don't just assume that what I get here is going to be an inflection point. It usually is, but not always. Now divide. X equal 1. Okay, so what do you do now? I don't know what to do. Take your second derivative. Now look, you could do this real simple. There it is. There's my possible inflection point. Now I'm going to pick test points. I could pick 0 here, but I'm gonna go. I'll pick -1, and over here I'll pick 2. These are my test points. Now I'm going to plug them in and check my signs. All All right, so I rewrote my derivative over there, my second derivative, since I'm going to plug in. Now, when I plug -1 in, for x, this is -2. Do I care what the number is? No, I don't. I know that it's -24. I understand. I don't care. I know that I get a negative when I plug -1 in. That means that the shape is going to be concave down. When I plug in 2 for x, well, 2 minus 1 is 1. Do I care that it's 12? It's 12. I don't care it's 12. I care that it's positive. Remember, you don't care, concave up. You don't care about the number. You care about the sign. So I know that from -infinity up to 1, the graph is concave down. And I know from 1 to infinity, the graph is concave up. Okay, so I wrote the interval where the graph is concave up from 1 to infinity, right? There's your region. From 1 to infinity, the graph, the shape of the curve is concave up. From -infinity to 1, the shape of the curve is concave down. Now, I need this point. We're going to cheat. I'm going to do it in my head. I'm plugging in 1. Where? Here. To the original function. That's where you have to plug it in. So just put 1 in there. I'm going to do it in my head, okay? 1 to the third is 1. So I multiply that by 2, I get a 2. 1 squared is 1 times -6, I get a -6. 1 times -36 is -36, and then you have a +1. Let me add up my positives here. 2 and 1 make 3. That's -42. So you get -39. Again, this would be crazy if you tried to graph this. You would not go draw 39 thing. You would just, you kind of cheat it. I make sure that the numbers come out nicer for you when I'm giving you one to graph. I'm not going to make you graph this ridiculousness. Okay? So, but this is important. You need to know the point. I took my second derivative. I had to take the first derivative before that. Second derivative, set equal to 0. Solve. Put that on a number line. Pick test points. Plug those test points into the second derivative. Determine your sign, whether it's positive or negative positive. Figure out if you have an inflection point. If you do, you plug it back into the original and you get the y value. Okay? I'm going to write a couple scenarios on the board and we'll discuss them. I decided to do a second one to show you what kind of weirdness can happen. I'm going to run through this one a little quicker and I'm not going to do the whole thing. I just want to show you. I'm going to take the first derivative because I need the second derivative. So it's 4x third plus 12x squared. Derivative 8 is, do I even have to say it? Second derivative, 12x squared plus 24x. Now I'm going to set that equal to 0 in a minute. Now I hope I don't have to point out that if you do something really ridiculous and dumbass and do this derivative wrong, you're screwed. So just be really careful. I'm going to set the second derivative equal to 0. I don't know how to solve this. It doesn't make any sense. It doesn't factor. There is a 12x in common that you're going to factor out. 12 divided by 12 is 1. X squared divided by x is x. 24 divided by 12 is 2. X divided by x crosses out, makes 1, right? Equals 0. So you get 12x equals 0, which means x is 0. And you get x plus 2 equals 0, which means x is -2. Now I'm going to put those numbers here on the number line. Be careful. -2 goes here. You do this backwards, besides the fact that it's ridiculously dumbass. You're going to screw up everything. I think I'll pick -1 in the middle there. And I think I'll pick 1 over here. Now, I'm going to do this a little differently. Now, when I say I'm doing this differently, this is what I actually do myself when I do this. I'm going to put -3, right? This is a product. You're multiplying it. -3 times 12 is negative. -3 plus 2 is negative. And a negative times a negative is a positive. Again, I don't give a damn about the signs. I don't even need to do this. -1 times 12 is negative, right? It's -12. -1 plus 2, so that's 2 take away 1. That's a positive. That gives me a minus. Now I'm going to plug in 1. Plug 1 in. You get 12 times 1, which is plus. And then you get 1 plus 2, which is plus. So I get positive, negative, positive. So this graph goes from concave up to concave down to concave up. So I would have 2 inflection points. 2! I'd have to plug them both in and figure out what the y values are.